want to do is go ahead and take care of exam, talk about the dates for exams being set at the end today, if you're okay about that. Now, look, we got Thanksgiving coming up. I don't care when you have the exam. I mean, I don't really care, it doesn't matter to me. I don't take it, I just administer it. But you know when your other exams are. So I'm looking for suggested dates. Now, we basically have most of the material done that we're required to do. Now we're going to do applications, the Z-transforms, applications, some other filtering methods, and see more or less, we're going to, after you get all this theory, what good is it? So you've seen a little bit about the Laplace transforms and how they can be used to realize actual circuits with, or really transforms with simple things like resistors, capacitors, and op amps. You can realize transfer functions. We're going to do this for the Z-transform today. We actually realize it, but then we're going to actually apply it to filter aspects of real-world problems, things like that. So, that said, what date would you like your exams? Now remember, give me the day, first give me the actual day of the week and the date. Yes?
The 14th, Wednesday.
November 14th?
Wednesday.
All right, so this is going to be Wednesday. And this is November 14th. Remember, the next week is Thanksgiving.
Yes, and then we only have one more full week, and then we have a half a week. after
What else?
that.
Yeah,
What?
good.
Friday, November 9th.
Oh,
It's
no,
back here.
please no.
That's in 5 days.
That's the
4 days.
day, though. That's the big day.
Right.
Oh.
No, it's not.
No way.
You're going to vote, what else?
That following Monday, I guess it'd be the 12th.
Monday the 12th.
Do we have class that day? It's Veterans Day. Do we have class?
Yeah, I didn't say we don't.
I honestly hope we do.
It was at least Friday the 16th.
You want Friday the 16th?
No. I can't do the first one.
Or the Wednesday after break.
It's the 12th,
Oh, yeah.
Anything else?
May well be your
Yeah, I think that's
test.
I mean, that's, I mean, we can play the game all day.
It's the 12th.
You know, my thoughts on Friday tests, but I don't care. This is your test. If you want Friday, more power to you. I just, if you have other exams on other days, I'm encouraging. Monday tests usually got the highest average score. That's what I can tell you from experience. I can't say it's always true for you, but it is true in general from everything I've seen. Because you have the whole weekend to study. All right. If you want the weekend to study. All right, now, how many want, we're just one hand, one time, all right? We're starting out here. How many want Friday, November 16? One hand, one time. I see one. I see two. Hold on. I see three. Just hold on now. I see four. Wow. That's
Stop racing, y'all.
now, you guys don't vote again. Count with me, all right? November 14th on Wednesday. One hand now. I got 2, 4, 5, 6. These
7.
2, 4, 6. Oh, I saw it. 7. All right, 7. Good. We'll run off the top two. Monday, November 12th. One hand now. 1, 2, 3, 4, 5, 6, 7. Do I see 7?
Yes.
All right. And Friday, November 9th. One hand. No, one hand.
Can we do a runoff?
So we're going to run off the two middle ones. All right, think about it for a second.
Question. All right, so we do have the test Wednesday. Will we have class Friday?
Absolutely. This is a monitored class. Understand? You have so many hours you must meet. If you don't meet, barring some natural disaster, then I get in trouble and you might not get credit. So remember that. I'm not kidding about this either. This is a serious deal with the university. It's state money involved in this stuff. So they make sure if you don't meet your classes, boy, you've been an act of God involved or something because you don't want it sitting alongside the state legislature. I'll be without a job and you'll be without 3 credits.
Mm.
I think, I mean, maybe I still will have my job, who knows? I'm beginning to doubt that. Anyway, the middle 2, now think about it for a second. So if you want it Monday, November 12th, one hand, hold them up there and I want, count with me. I got 1, 2, 3, 4, 5, 6, 6? What, wait, 2, 4, 6. That's it, right?
Y'all need a test?
Wow, all right. Wednesday, one hand out, one time. 2, 4, 6, 8, 10, 12, or 13. All right, it is.
Yeah.
I'll give it to you Wednesday. Anybody go to the game? Anybody see a miracle happening?
Because it's a weekend.
All right.
Thank you.
That's Wednesday, November 14th.
He still got Wednesday or Friday to tell us we got a week left.
All right, I got 2 things to talk about. I left my notes set at home, but I'm not going to need it for this one. The first is going to be, it starts on page 378, and it deals with solving differential equations and something called the zero state and zero input response. Now, I'm going to explain something. In this, on page 379, he has something where he has a y of t, not a y of n. Don't worry about that. The same thing he's talking about also applies to y of n in x of n. He just somehow did this little mess up. So he's going to say, in general, if you have a system, and I'm going to call it y of n, that will be given as, he calls it the 0 y, CR of n plus y, and this is ZIR, pardon me, ZIR, zero input response, and y, zero state response of n. Now, let me explain this and get a better, and what he's saying. And I'll do an example. In general, if you have a system, any system at all, where you have some x of n going in to the system, and this system has some h of n here, the corresponding output y of n is equal to x of n involved with h of n. Or you can have x of z going in, have an h of z, this is in the transform domain, your output y of z is simply x of z times h of z. This is the one we like. Now, when we're looking at this right here, y of z equals x of z times h of z here, and we go ahead and do this. Suppose we take x of z and multiply it by h of z. We get this, then we go back to the time domain. There are certain things that happen in there that are implicit. One is there are initial conditions. There's like a y of -1 possibly, a y of -2, and so forth. These are the initial conditions. Or it has to do with, now what we're going to talk about is a zero input response, but we're going to find out what the output is for the initial conditions. So just listen to me, I'm going to try to make sense of this to you. When we take a look at the solution, right here, y of z, and it will go back into a y of n. We can say that y of n is actually the solution of that system that I'll show you how to do in a second, to nothing more than the output due to the initial conditions, which would be the output y here, and it would be due to y of -1, comma, y of -2, etc. So it would be really an output due to this. And I'm just going to leave it like this. Understand the output due to that. Plus, it would be the output due to zero initial conditions, or no initial conditions. But just x of n for n greater than or equal to 0. Follow me on this one? The output can always be gotten from just the system response to the initial conditions without any x event. Follow me? If you just had the stored energy in the system and you let the system respond just to the stored energy, you're going to get an output response. Once you have that, then you can add to that the response of the system to the input. In other words, to x event. Does this make sense to you people? I'm going to do an example. You're going to see. Now think about this in terms of an RLC circuit. If you're getting an output to an RLC circuit and you have an input, some x of t is the input, and you say you're measuring the output across the resistor, the voltage, you can say that output is due to the initial stored energy decaying. Follow me? Like the energy on the capacitor and the initial current in the inductor. Plus the output due to the actual driving voltage for t greater than 0. And you can add those two. Does that make sense to people? Well, it's the same thing when you're dealing with a system like this. I didn't do this very well. There's a formal way to do it. But I'm going to say y of n is going to be due to just the response of the system to the initial conditions. Y of -1, y of -2, and so forth. That's the stored energy. Plus the output due to just the input, just x of n, assuming 0 initial conditions. Does this make sense? I'll do an example and you'll see this, hopefully. The book makes it a little more exact, but they have it in a goofy way, but they're just saying it's 0 input and 0 state responses added together. So in the book, and let me do 716 for you. This is example, I think, for exercise 716.
What page was the first thing you?
This is all page 378, 379. And this is exercise 716. Here, they have y of n minus 2y of n minus 1 equals 3x of n plus 4x of n minus 1. And he gives a condition x of -1 is equal to 1/2. This is an initial condition, by the way. This is something that he states. So he has x of -1 is 1/2. And he wants compute the 0 input response to the system when y of, no, I'm sorry, it says y of -1 is 1/2. Sorry, I have x is y. All right, that means this is an initial condition. It's stored energy. Think of it as stored energy. Follow me? Now, we're going to go through this. First thing we're going to do is take the Z transform of everything. Understand? Take the Z transform of this. And in doing so, what we end up getting is what? When we take a look at this, actually we can do one better. Since he said there's no input, right? Correct, class? He says there's no input. We can just get rid of this if there's no input. There is no x of n, right? There is no x of n minus 1. Follow me? So you might as well just make this 0 for now. We're just getting the response, the 0 input response. No x of n, just how the system responds to the stored energy. So if we do this, we take the Z transform of this and we get what? Y of z, right? Minus 2 times the quantity of z minus 1 times y of z, right? And then it's going to be plus y of minus 1, all equals 0. Get out of the way. You all agree with that? That's a simple Z transform when there is no input, no x of n. Do you agree, class? You follow me on this one. I x'd out. I zeroed x. No input. Now, when I do this, I'm going to just go ahead and take it down here, and now I have my y of z, right? Minus 2 times z minus 1, y of z, minus 2 times 1/2, or minus 1, equals 0. Follow me what I'm doing? I have 2 times y of, or times 1/2 is simply 1. Can everybody see this? There's no tricks here, this is a straight one, it's very easy to understand. Now, once I do that, I'm gonna take 1 to the other side. Do y'all see what I'm doing here? Simply take the minus 1 to the other side, make it a plus 1, right? No tricks here, just trying to show you how you use this. Now, after that, y'all see I can factor y of z out of that thing, right? So then I have y of z here is equal to 1 over the quantity 1 minus 2 times z minus 1. Agreed? Just make sure you see what I'm doing. Agreed? Finally, I can say that's equal to z over z minus 2. And what do you know that response is? By your knowledge of the transform pairs. It's going to be simply 2 to the n u of n. Agreed, class? That would be the zero input response, VIR. There is no input, just the actual stored energy is responding. The system is responding to the stored energy. All right? Now, I'm going to go to the second. I don't think he does this in here, but he should. Now I'm going to go ahead and I'm going to put in an x of n. Back, I'm going to go to the original equation. This right here would be the zero input response. Just box that. Now, he doesn't do this one. This doesn't give you it, but I'm going to go ahead and give you now a value of x of n. So we can do this problem properly, all right? Now I'm going to say the actual input to the system was x of n is equal to, say, u of n. I'll make it anything you guys want, but u of n is probably as easy as any. I can make it a to the n u of n, but u of n is fine, right? Now follow me on this. Now I'm going to go put in what was here that I erased, which is 3 times x of n plus 4 times x of n minus 1. Matter of fact, why don't I do it here? So I have, I'm going to go to the original one. I have y of n, right? And then it's going to be minus 2 times y of n minus 1 is equal to, help me out here, was it 3 times x of n?
Yes, sir.
Is it minus or plus 4?
Plus 4x of n.
N minus 1. Agreed? Now here there is no input. No initial conditions. Just the input. Follow me? Now we can go ahead and do it formally. When we do this, when we take a look at this, right? This right here. Now we get y of z, right? Minus, and this is 2 times z to the minus 1 y of z, right? Remember, we ignore the y of minus 1 here. Follow me? It's 0. We assume there's no stored energy. Is equal to 3 times x of n, and we can just put it down, 3 times x of z, if you want. All right, plus 4 times z to the minus 1 here of x of z, right? Now that, the only thing I've done is taken the z transform of both sides. Do you agree with me here, class? Now when I look at this, I can say for this one particularly, I can say this is x of z here times the quantity 3 plus 4z to the minus 1 on that side. And on this side, it's y of z, right, times 1 minus 2 to the z minus 1. You agree with me? I could have gotten in terms of the transfer function. I don't even need to on this one. You all see what I've done so far? Simple z transforms. Now, what is x of z if x of n is u of n? Z over z minus 1. Do you agree with me? I'm going to put it in there. So this is going to be z over z minus 1 times the quantity 3 plus 4z to the minus 1. And I'm going to divide this by 1 minus 2 to the z minus 1. And that would be y of z. first just see, it's sloppy on purpose, all right? I made sure that I've got a lot of things wrong, so I'm gonna make them right by doing something. Multiplying top and bottom by z in 1 second. Y'all see what I'm doing here?
What happened to the one? Because y to the minus.
2 minus, or 1 minus 2z to the minus 1? 1
Not
minus,
not that
There
one.
used to be a, yeah, in the very,
where?
The initial condition.
Oh, there's no initial conditions. This is the zero state response. There is no initial conditions to this one. We did the initial condition response, right? That was the zero input response. This is the zero state response. State means how much energy is in the system. There's no energy stored before this thing is turned on. Follow me? No initial conditions. So now when you look at this, I don't care how you do it, but probably when I see this, multiplying top and bottom by z would be a good idea. Do you agree with that? And you know, even before I say that, I mean, you could break this out. There's 2 fractions here, but if you multiply by z, I get rid of this, I get rid of that. I put a z down here. And then I make that 3z. Y'all agree with me there, class? Right? Now, how do you want to solve this? There's actually a couple ways. You all see the factors here are just z minus 1, z minus 2, right? Now, what is normally done here, because what I see is the power of the numerator, the highest power is going to be z squared, the denominator is z squared, is divide by z. Remember, that was always take y of z by z and do the partial fraction before you actually multiply by z and get the actual. How many remember me doing this? All right, I'm going to erase this and do it over here. The problem I'm showing you is very, very, it exposes all the things you need to consider when doing these kind of problems. But it's going to make it a lot easier than doing it all in one fell swoop, breaking up into 2 parts. Response to the initial conditions and then the response to the input. This is always the easiest way to do these problems. So now what I'll do with this one is say y of z over here. We'll do it together. I'm going to break out the first fraction, which is really 3z squared over z minus 1 over z minus 2. You don't have to do it this way, but I'm going to do it this way. Plus 4z over z minus 1, z minus 2. Now some of you put it all under a common denominator, and you can do that. Matter of fact, I tell you what, I'm going to do it that way because I did it this way before. So I'm going to go ahead and put plus 4 here, 4z here. And then I'm going to say, I'll just leave it with a common denominator, but now I've got to divide by z, right? When I divide by z, I get this, and I know that this will be equal to some constant a over z minus 1, right? Plus b over z minus 2. We'll do it that way. Last time I broke it, I did it 2 separate fractional forms and combined things at the end. Do y'all agree with me this way? This is probably easier to tell you. All right, how do we get a?
u z equals 1.
Cover this up, right? The pole is at z equals 1, right? When it's 1, I have 3 plus 4 is 7, right? I have 1 minus 2 is minus 1, so it's minus 7. Do you agree with that, class? So I'm just going to put it up there. This is minus 7. How do I get b?
Z equals 2.
So cover that up. When z is 2, I have 2 minus 1 downstairs is 1. And then I have 3 times 2 or 6 plus 4 is
10.
10. Now, if y'all give me that, agree with me, now I multiply by z, correct? I've divided by z to do the partial fraction expansion. If I multiply by z, right, now I have this. Agree? And this goes back as what, people? Minus 7 times what? Times u of n only, right, class, for that one? What about the next one? Plus 10 times
2 to the end.
there.
2 to the n
U
of n. And that would be the actual output response to the zero state. I mean, you're gonna, sorry, to the zero initial conditions. You add that to the original one, and now you have the complete response of the system. Now, I put a U of n in here. There's something that you should take a look at. It would bother you about this. It should naturally bother you. Take a look at that. What happens as n gets large? It's going to infinity, right? This would be an unstable system output. And unfortunately, that happens a lot of times when you're building, or when you're doing things in modeling, you see instabilities you didn't see before when you do the entire modeling of that. But for a certain set of inputs, the output would be stable. For instance, if the input was 0, the output would be stable. We saw it was what, 1/2 to the n U of n, right? Isn't that what the first part? We'd have to add that solution to this. The total solution would be this, total plus 1/2 to the n U of n. Didn't we just calculate this in the first part, class? Y'all remember that? Wasn't it? Oh, I'm sorry, it's 2 to the n. My bad. 2 to the n. Well, that's unstable too. So that means just by the initial condition, just the initial conditions let loose would cause an instability, which is not good. Anyway, but that would be the total input, that would be the output for both the zero input response and the zero state response. And this, in fact, is the total Y of Z. I mean, Y of N, pardon me. And that's really exposes what you need to know about that. Now, you can see for this type of problem where you have both Y and X with delays, right, you could get an X of -1 as well, couldn't you? And you would have, yes?
You were saying if we don't add on the 2 to the end, that is the same thing without the initial?
This is just what? That is the zero input response, right? This is the zero state response. This means you ignore initial conditions. You just take a look at how the output is affected by the input. Here, you ignore the input signal entirely. You zero it out and just see how the output is affected by the input, the initial conditions of the system. You add them together, you get the total response of the system. It's easier to do it this way, mainly because of this reason. Y'all know if you get a transfer function here, you got a lot of y minus 1, y minus 2, x of minus 1, x of minus 2, plus you have the actual x of z as the input. You can get a really complicated mess that you have to do a partial fraction expansion on. This way, it eliminates or reduces that complexity. So remember, I'm trying to help you. In the book, he talks about this. It's a very good way to do business, is what I'm trying to tell you. Makes it much easier. You've seen things like this before with your differential equation solutions. I didn't harp on it, but you can always find the output for what? Just the initial conditions, and add to that the output for the actual input with zero initial conditions. That's the complementary solution of the specific route. You can do that. All right. That went well. I didn't ask this, but were there any questions about the homework before I get there? All right. Prior homework. Prior homework. None? Okay. I just hope you're caught up with all that stuff. All righty. Next is implementing these things. How do you actually build stuff? This is shown on page 381. And I'm going to try to do this for an example in here. This is going to be, let me show you how to build a circuit, or build a system, an actual system. Y of n minus 0.6 y of n minus 1 plus 0.08 y of n minus 2 is equal to 4x of n. It has zero initial conditions obtaining the transfer function and a block diagram to actually create that. Now, since it's got zero initial conditions, the y of minus 1, y of minus 2, we don't have to worry about, right? So we come down here and take a z transform of both sides, and I have now y of z, right, times 1. And then I'm going to have minus 0.6 z to the minus 1 times y of z. Remember, there's no initial conditions, plus 0.08 z to the minus 2 here, y of z, is equal to 4 times x of z. And that's straightforward. There's nothing, there's absolutely nothing tricky about this. Now, here's the one thing you remember. Z to the minus 1, z to the minus 2 really means a delay. The only thing you are is delaying the actual output by 1 count. If n is 1, at that point, then the output be at n equals 0, prior to 0, right? You just delay. The way they do block diagrams is this. First, before we actually put with delay lines, this is shown on page 381. And what we do is this. You take a look at this, right here, and you start with y of z as the output. You always start the output. Y of z over here. Now, what affects it? First of all, it's 4 times x of z, right? So if this is x of z here, you just put a block in and put the 4, and then an arrow to show you the actual direction of the signal flow. 4 times that goes to here. But before it comes there, put a little summer there. This is the way I like doing it, at least. That's going to come to the output, right? Now the next thing that happens is, also it's minus 0.6 z to the minus 1, right? So what you end up doing is this. Here, erase that. Make it a little noise. Now I take this, and I have z to the minus 1 as the operation. I know that's going to be a delay line when you come back to the time domain. And then I have minus 0.6 here. And I take that, and I feed it back here to this point. Now you look at this, there's z to the minus 1 times minus 0.6, which is this part right here. And I'm adding it here with the summer to what's already there. Follow me? Can everybody see what's going on here? After that, I come down here and I have another block with z to the minus 1 here. And then I have 0.08. And this is the flow of the signal. And this is going to come up here, and it's going to be added there too. So I showed a summer with 3 inputs, and you can see that this implements, in fact, exactly what this is. Y of z here is defined as, oh, I'm sorry, hold on, I made a mistake here. I made a mistake. I should have taken these to the other side. My bad. This should have been minus or plus 0.06 z to the minus 1 y of z, my bad. And it's going to be minus 0.08 z to the minus 2 y of z here. That's what it should have been, and these would have been taken up. Everything has to be on the other side. So first one was the 4 times x of z comes in as y of z. Then it's going to be plus, not minus, plus 0.6 times z to the minus 1, right? Y of z is here, comes back in, and then z to the minus 1 gets to z to the minus 2 times 0.08 right there, and this is going to be a minus right there. And that would be y of z. I'm sorry about that. Didn't take it to the other side. But that's the flow, and that's the general idea behind this. Now you see this parallels what we did before when we did the actual H of S, and we had the 2 methods of actually implementing it. You remember? Where we had negative feedback, we used it. Here we didn't use negative feedback. We just used a simple equation and did a block diagram form like that. And this is completely legit. You don't have to have a negative feedback block. But this will do this, in the Z domain. Now, hear me. If you go to the actual N domain, then these would be replaced by the symbol D. You'll see a capital D right here. And what these are is delay lines. So whatever is coming in here, the output is the value of this input delayed by 1 count. So this is a clock cycle thing. You know how you have your clocks, they're cycling through? And as they cycle through, what that is really, a delay line simply holds the value back by 1. It's a memory register and then pushes it out with a simple delay of 1. It's very easy to implement this, and this is sort of the beginnings of implementing real digital filtering. This is a real-time filter, and then this would be, when there are delay lines, this becomes Y then, and this becomes X event. And you can, yeah.
We changed the D to like a D to the -1?
Now, D is a delay. A Z to the -1, where did it come from? It came from a delay here, didn't it? All right, when we did the Z transform, so wherever you see a Z to the -1, that's a delay of 1. Z to the -2 is a delay of 2, so we put 2 delay lines in series. Now, I'll just tell you one thing. The actual digital filters that we're going to end up dealing with, there's so many variants to this. I'm going to show you one that is basically a low-pass filter in the digital domain. And the only thing it does is have a running sum of, it has a value of a running sum, and it's averaging more or less. This is used for stock market data manipulation a lot of times. They want to see general trends and not the day-to-day variations. This is the simple low-frequency filter I want to show you. And I'll do it in the Z transform. We'll take a look at the actual the shape of the in the frequency domain of versus omega. But this is difficult. If you think of this is really applicable to stock market, or whenever you get really noisy data and you're looking at specific stuff at the low frequency range. I can show you bandpass filters later in the digital domain. But let's just assume we're dealing with the stock market for now, because this is the one that keeps on coming up and up. So we're going to come up with, stock market. If you looked at, say, the Dow Jones Industrial Price Index, and this would be Dow Jones, and it will do something like this. It's erratic, neurotic, and stuff like this, versus days of the month, right? It does all sorts of things. But there might be in here some overall trend we'd like to see, all right? Say over the order of months or weeks or maybe even years. So what we can do is say, I'm going to design a filter so my Y of N, the I pick of this filter, is going to be 1 over N times the summation of X of N here, N equals, say, I have to do this with a K over K plus capital N. Now, I'm sorry, this is Y of K here. Pardon. Now I'll explain this in a second. K is the day of the month, or a day of the year, pardon me. Day of the year. So there's 365 days in a year. Now what this is it's really taking a value. Remember, it's a running average. So it starts at some value K, say 2. And it's going to add all the values of X of N, or really X of K, X of K plus 1, X of K plus 2, X of K plus 3, all the way to N. Follow me on this, class? So it's going to take an average, say, from wherever the start is, the next 3 values, 4 values, 5 values, and it's going to average them out. Does that make sense to everybody? It's a running average. If that's going to be my value, Y of K. Now, what that is really doing, that averaging, it's causing a low-pass filtering action. Here's how we can see it. What would be the transform of this in the Z domain? I know you would like that as an N, wouldn't you? I can probably make that an N. and then let this be k equals n to small n plus capital N, make that k. That way, a lot of times it's I as well. That way it looked like the proper Z transform. Follow me on this? Now, what's the actual transform of this? Who did this one? Say again? You remember how, what this looks like is a sum, doesn't it, class? Isn't this a summing function right here? So when you have a summing function, well, how do we always do this? We'd say that this could really look like what? Since this is y of, this is the definition of y of n, I could say y of n look like y of n minus 1, that's one less value, plus what? X of n. Follow me on this one? Now I break out the last value. Do y'all remember this for sum? How many do right here? Right? And if you follow me on this, we could actually do the Z transform of this identical. But if you look at this, let me do one thing here. First, let me make it a little, before I show you this exact one, I'm going to take it back a notch and just show you. Suppose I define y of n equal to just the sum from n equals 0 to capital N minus 1 of x of n. And I want the Z transform of that. You remember what that was? That was really the summation. I can go from 0 to n minus 1. That's really equal to what? The summation here from n equals 0 to n minus 2, right? Of x of n plus x of n minus 1, right? The last data point. Isn't that it? Agree, class? Just watch on this. Do y'all agree with that? Now, when I look at this, what do I have here? This is really what? This is like y of n equals y of n minus 1, right? Plus x, I've used a capital N. I'm going to limit this x of n there. Let me do it this way. Just go to n there. Make that n minus 1. It's x of n. And this would be actually I. That would be better this way. Leave it like that. Here, I'll just tell you what I'm trying to do is get these to be a summing where I don't want to use. Let me do it the way the book did it first. Sorry. I call y of n identical to the book equal to the sum of x of I. I goes from 0 to n. That's the way the book did it. That should make sense. Now everything's in terms of n, right? It's just the sum up of n. I can say this is really equal to the summation here, I equals 0 to n minus 1 of x of I plus x of n. This is the way the book does this. This will be neater. Y'all follow me in this class? I just picked off the last value. Now, what is this really? Well, that's y of n minus 1. So now I can say that y of n here on that side is really equal to y of n minus 1 plus x of n. That's where I wanted to go with this. I'll modify it in a second. I'm trying to show you this filter. This is a sum, right, of all the values. Now when you take the Z transform of this, you get y of z here is equal to z to the minus 1. We're assuming no initial conditions times y of z plus x of z. And here I've just did the Z transform of both sides with no initial conditions. And then I go ahead and I get y of z here, 1 minus z to the minus 1, right, is equal to x of z. And I get the transfer function y of z over x of z is equal to h of z, is equal to 1 over 1 minus z to the minus 1 is equal to z over z minus 1, or simply y of z here is equal to z over z minus 1 times x of z. Now, bear with me, I'm out of time and I didn't want to take that much time here. That right there tells me that whatever x of z is, it's weighted by z over z minus 1 to get y of z if I have this summing thing. Now, on a running sum, here's the deal. I mean, this will be true for anything, but on a running sum, then this index here will have some point other than 0, right? It's going to start at this point out to that number of counts, capital N minus 1. I won't deal with it any longer than this. When I take a look at this right here, this x of z right there really is going to look like the DFT of the actual original data, the values of the stock market day by day. You can easily take a DFT of that. Do you follow me on that? When you multiply it by z over z minus 1, or 1 over 1 minus z to the minus 1, either one, this right here looks like 1 over 1 minus e to the minus j omega. If you take a look at that, just plot this right here. That's like your the h of omega. If you just look at this for a second. It actually probably should put a value of rho here, but you're going to get a maximum value of 1 over 1 minus rho here, and then as this angle gets larger and larger, it goes down, and this will become like additive. When this is at e to the minus j pi, that's minus 1. Minus 1 with a minus sign is plus 1, so it goes down to a minimum value with pi or at minus pi, and this is a low-pass filter is really what I was going to show you. I'll speak more about that next time, and I'll show you on Wednesday. Also, we did realization, but with some more examples of it, and some real filtering examples. Sorry, I hung up on that one. I need to